Director of the White House Office of Science and Technology Policy, Dr. Kelvin Drogemeyer, and from the National Science Board, the current chair, Diane Sylvain, and former chair, Maria Zuber. Today, the Event Horizon Telescope Project will announce findings that will transform and enhance our understanding of black holes. As an astrophysicist, this is a thrilling day for me. Black holes have captivated the imaginations of scientists and the public for decades. In fact, we've been studying black holes so long that sometimes it's easy to forget that none of us has actually seen one. Yes, we have simulations and illustrations. Thanks to instruments supported by the National Science Foundation, we've detected binary black holes merging deep in space. We've observed the episodic transfer of matter from companion stars onto black holes. Some massive black holes create jets of particles and radiation. We've spotted the subatomic neutrinos those jets can fling across billions of light years. But we've never actually seen the event horizon, that point of no return after which nothing, not even light, can escape a black hole. How did we get here? Through the imagination and dedication of scientists around the world, willing to collaborate to achieve a huge goal. Through a large pool of international facilities, and through long-term financial commitments from NSF and other funders willing to take a risk in pursuit of an enormous potential payoff. Without international collaboration among facilities, the contributions of dozens of scientists and engineers, and sustained funding, the Event Horizon Project would have been impossible. No single telescope on Earth has the sharpness to create an unblurred, definitive image of a black hole's event horizon. So, this team did what all good researchers do. They innovated. More than 5 decades ago, other NSF-funded researchers helped lead the development of very long baseline interferometry, which links telescopes computationally to increase their capabilities. This team took that concept to a global scale, connecting telescopes to create a virtual array the size of the Earth itself. This was a Herculean task, one that involved overcoming numerous technical difficulties. It was an endeavor so remarkable that NSF has invested $28 million in more than a decade, joined by many other organizations in our support, as these researchers shaped their idea into reality. I believe what you're about to see will demonstrate an imprint on people's memories. The Event Horizon Project shows the power of collaboration, convergence, and shared resources, allowing us to tackle the universe's biggest mysteries. And now I'm going to hand over this to our distinguished panel, starting with Dr. Shep Doleman, EHT's director.
很快的翻译一下，就是刚刚他致辞的意思就是说，他身为一个天文物理学家，那他很高兴看到这个结果，因为我们都已经为了这个研究黑洞尽了非常多的时间，那终于我们在今天看到一个成果，那这个成果是属于这个长期投入在这个研究上面的没有这些长期投入的经费跟人员，我们是没有办法得到今天的结果。那现在致辞的这位是叫做 Shep Doleman， 那他是这个整个 EHT 计划的计划主持人。
The best idea we have of what they can look like.
Hello, Chief.
Like this. The infalling gas that's superheated lights up a ring of light where photons orbit the black hole. And interior to that is a dark patch where the event horizon itself prevents light from escaping. The Event Horizon Telescope project is dedicated to the idea that we can make an image of this black hole, that we can set a ruler across this shadow feature, measure the photon ring, and test Einstein's theory where they might break down. It also will allow us access to a region of the universe.
各位媒体朋友，现在您在画面上所看到的是由电脑模拟所产生的黑洞影像。这是由电脑模拟所产生的黑洞影像。我们如果在附近黑洞的附近有强烈的喷流或是一些物质，那掉入在视线地平线之内，就是产生这个模拟的影像。这是电脑模拟的影像。
highest angular resolution possible from the surface of the Earth. It's the equivalent of being able to read the date on a quarter in Los Angeles when we're standing here in Washington, D.C. In April of 2017, all the dishes in the Event Horizon Telescope swiveled, turned, and stared at a galaxy 55 million light years away. It's called Messier 87 or M87. And there's a supermassive black hole at its core. And we are delighted to be able to report to you today that we have seen what we thought was unseeable. We have seen and taken a picture of a black hole. Here it is.
这就是我们人类首次看到的黑洞的影像。
Is that true?
This is a remarkable achievement. What you're seeing here is the last photon orbit. What you are seeing is evidence of an event horizon. By laying a ruler across this black hole, we now have visual evidence for a black hole. We now know that a black hole that weighs 6.5 billion times what our sun does exists in the center of M87. And this is the strongest evidence that we have to date for the existence of black holes. And it is also consistent, the shape of this shadow, to the precision of our measurements with Einstein's predictions. The bright patch in the south that you see tells us that material moving around the black hole is moving at light speeds, which is also consistent with our simulations and predictions. And this image forges a clear link now between supermassive black holes and the engines of bright galaxies. We now know clearly that black holes drive large-scale structure in the universe from their home in these galaxies. And we now have an entirely new way of studying general relativity and black holes that we never had before. And as with all great discoveries, this is just the beginning. So imaging a black hole doesn't come easily. I can tell you that from personal experience, as can many people here in the audience. It's required long-term developments, a committed team, but it also required some very interesting cosmic coincidences. Take, for example, the maelstrom you see before you, like the hot gas swirling around the black hole. A photon has to leave from close to the event horizon, travel through the hot gas in falling to the black hole, and light rays of a millimeter wavelength, radio waves, can make that journey. Not all of them can. Then that radio wave has to propagate 60,000 years through the M87 galaxy, and then another 55 million years through intergalactic space. And then it winds up in the Earth's atmosphere, where its greatest enemy, the greatest danger, is that it will be absorbed by water vapor in our own atmosphere. So the Event Horizon Telescope uses telescopes at high dry sites so that we can see the photons that have traveled to us so far. So far, so good. We have the photons. But the M87 shadow is very, very small compared to the galaxy that surrounds it. So in order to see it, we needed to build a telescope as large as the Earth itself, given the wavelength of light we were trying to observe. And to do that, we use a technique called very long baseline interferometry, which you can see a schematic of here. Radio waves from the black hole hit radio telescopes, where they're recorded with the precision of a time clock.
现在解释的就是我刚刚讲，我们必须要让在地球两端
When you've registered these radio waves so precisely, you can then
同时
store them
观测我
on
们的
hard
目
disk
标
drives,
黑洞，
send them to a central
然后
facility
再
where they
把
can
这两
combine
个望远
precisely.
镜或是
It's
更多望
exactly
远
the
镜的
same way
讯号
that a mirror using
集
an
合起
optical
来
telescope
来
reflects
分
light
析，
perfectly
让
and
它能够达
synchronously
成
to a
像一
single
个
focus.
地球一样大的镜
And
面
when we
一样
do
的
this,
观测效
we
果
can。synthesize a telescope that has the resolving power, as though we had one the size of the distance between these telescopes, truly turning the Earth into a virtual telescope. All the sites that we used can be seen here. We have telescopes from Hawaii to Arizona to Mexico, to Chile, to the South Pole, and Spain.
那这也是我刚刚提到的，就是我们在这个计划里面呢，在夏威夷的 SMA 跟 JCMD， 还有在智利的奥马，都是我们中央研究院的
During a night of observing, we are able to send out more baseline.
那另外的观测还有在西班牙、南极、美国，还有墨西哥。
You'll see the Earth turning. Every pair of telescopes provides us with one point on the center panel, which fills in the Earth-sized virtual lens. And on the right, you see the evolving image. The more and more data we get, the more we fill in this virtual mirror, the sharper our view of the black hole becomes until you wind up seeing what we have as the final image there. So we've taken advantage of a cosmic opportunity.
Yeah, it's
remarkable when you think about it. Light that left near the event horizon, traveled all the way through intergalactic space. It hit our telescopes. The Earth just happens to be the right size. So we get resolving power so that we can see the black hole in M87, whose mass and distance let us observe it. And then the Earth turns to fill in our mirror so that we can make this image. It's truly remarkable. It's almost humbling in a certain way. And we are 4 members of a large collaboration, and it is our distinct honor to be here to represent that collaboration. We are 200 members strong, we have 60 institutes, and we are working in over 20 countries and regions. We consider ourselves really to be explorers. Through international cooperation and innovation, we've exposed part of the universe that we thought was invisible to us before. It's our responsibility now to report these findings, and we're doing that today to the National Science Foundation, to our funding agencies, international and foundations, and to all people who support pioneering research, and also to the taxpayers. Nature has conspired to let us see something that we thought was invisible. This is a long-sought goal for us, and we find it tremendous, and we hope that you will be inspired by it too. Thank you, and now let me introduce Dan Maroney, who has literally gone to the ends of the earth to collect some of the data that we've seen here today.
好，那我们跟美国连线就到这边结束。那接下来。